So now when we have studied about permutations and how to operate different permutations, we will be studying about how S3 is a group with operation of function composition. So what is S3 basically? S3 is the set of all permutations on the set 1, 2, 3. Alright, it is basically the set of all permutations on the set 1, 2, 3, and we already saw that it comprises these permutations 1, 2, 3, 1, 2, 3, 1, 2, 3, and then 1 is mapped to 2, 2 is mapped to 3, 3 is mapped to 1. Then 1, 2, 3, 1 is mapped to 3, 2 is mapped to 1, and 3 is mapped to 2. Is it right? Or yes, it's right. This is the third permutation we did, and then 1, 2, 3. Let us keep 1 fixed and interchange 2 and 3, and then 1, 2, 3, keeping 2 fixed. The image of 1 is 3 and the image of 3 is 1, and then 1, 2, 3, the image of 3 is itself and the image of 1 is 2 and 2 have its image 1. So this is what S3 is. Now let me write the elements of S3 in cycle form. Alright, where for identity I will be simply writing I. Okay, I will not be writing it as 1, 2, 1, 2. I will write it as I itself. Now this permutation is 1, 2, 3. This one is 1, 3, 2. Now this one is mapped to itself, so 1 fixed, and 2 is mapped to 3, 3 mapped to 2. So I have 2, 3. Now this permutation is 1, 3 and 2 is fixed. Then 1, 2 and 3 is fixed. So these are the permutations in cycle form, and now we know that if we have any permutation in cycle form and the element is mapped to itself, that is we are getting a cycle of length 1, it can be avoided. There is no need to write that particular cycle. So we have the elements of S3 as I, 1, 2, 3, 1, 3, 2, then 2, 3, 1, 3 and 1, 2. Okay, so these are the elements of S3. Now we have obtained the elements of S3. Now we have to show that these elements actually forms a group with operation of function composition. So for that, now we have to verify that if we are having a group, if we want to show that say set G with some operation star is a group, then we have to show that it satisfies closure property, associativity, then the set have some identity element, with respect to the binary operation defined, and every element in the set has inverse. So inverse exists for all elements in G. Okay, let me write like this. So now we have to show that these four properties are getting satisfied. So let us start with closure, and in fact it is better to show that it is a group using a composition table. Composition table, or even known as Cayley table, we will show using the composition table that actually S3 forms a group. So let us show that S3 is a group. So for that, like, let me draw a table. Let me put identity here. Then 1, 2, 3, 1, 3, 2, 1, 2. Then what was the next element? 1, 3 and 2, 3. 1, 3 and 2, 3. Okay, let me write like this. So identity 1, 2, 3, 1, 3, 2, 1, 2 and 1, 3, 2, 3. So this is what we have. Now say I am putting an element, I am writing some result here. So what does it mean? It is basically equal to 1 2 3 1 3 2. Alright, and now if it is written like this, we know that we will be operating the permutation from right to left. So here we will be saying 1 is mapped to 3 and here 3 is mapped to 1. So the cycle closes. Now let us consider 2. 2 is mapped to 1 and 1 is mapped to 2. So the image of 2 is 2 itself. Now for 3, 3 is mapped to 2 and 2 is mapped to 1. 3 is mapped to 2, 2 is mapped to 1. 2 is mapped to 3. 3 is mapped to 2 and here 2 is mapped to 3 again. So 3 is mapped to itself. So this is basically the identity permutation. So here in this place we will be putting the identity permutation. Alright, so this is how basically we will be operating. Now I with I will be equal to obviously I. So here we are having identity. Now identity I with 1 2 3 will be 1 2 3 itself. Now I operated with 1 3 2 will be giving us 1 3 2, here 1 2 1 3 and 2 3. You can operate and you can find them out. Now 1 2 3 with I will again give us 1 2 3. Alright, so here we will be having 1 2 3. Now let us see 1 2 3 with 1 2 3. What is it equal to? Now see 1 is mapped to 2 here and here 2 is mapped to 3. So the image of 1 is 3. Now let us see what is the image of 3. So 3 is mapped to 1 and 1 is mapped to 2. So the image of 3 is 2. So we are getting 1 3 2 here, and so here we are having 1 3 2. Alright, so this is the next element. Now 1 2 3 1 2. What is this equal to? So again let us find what is the image of 1. 1 is mapped to 2 and 2 is mapped to 3. So the image of 1 is 3. Now 3, let's find what is the image of 3. So 3 is mapped to itself in this permutation and here 3 is mapped to 1. So the cycle closes. And now for 2, you can see that 2 is mapped to 1 and then 1 is mapped to 2. So 2 is mapped to itself. So this is 1 3 itself. So we are having 1 3 here. Alright. So here we are having 1 3. Now 1 2 3 with 1 3 gives us 1 mapped to 3, 3 to 1 itself. So the cycle closes. Let us find the image of 2 first. So 2 is mapped to itself and then 2 is mapped to 3. So 2 is mapped to 3 and you can find that 3 is mapped to 2 also. So this is basically the cycle 2 3. So we are having cycle 2 3, and when you will do the calculations, you will see that 1 2 3 operated with 2 3 will give us 1 2. Alright, you can find it out. You can do the calculations and you can find it out. Now here we will be having 1 3 2 obviously. Now let us see what happens when 1 3 2 is operated with 1 2 3. So 1 3 2 operated with 1 2 3 gives us, let's find out, 1 is mapped to 2 and here 2 is mapped to 1 itself. Alright, so 1 is mapped to itself. Now for 2, 2 is mapped to 3 and 3 is mapped to 2. So the image of 2 is 2 itself, and similarly you will find the image of 3 is 3 itself, and therefore it gives us I. Alright, the identity permutation. So this is what we have obtained here. Now 1 3 2 operated with 1 3 2. What will it give? Alright, you can try to find it out and you will see that we will be getting 1 2 3. We should get 1 2 3. Okay, so you can see that we will be getting 1 2 3. Now similarly, when you will find 1 3 2 mapped with 1 2, you will find that we will get 2 3. Then 1 3 2 operated with 1 3 will give you 1 2, and 1 3 2 operated with 2 3 will give you 1 3. Okay, it will give you 1 3. So this is how we will get the elements in the third row. Now similarly we have to fill the fourth row. So let us see what is 1 2 operated with 1 2 3. Okay, let us see what is 1 2 operated with 1 2 3. So let's find the image of 1. 1 is mapped to 2 and 2 is mapped to 1 itself. So the cycle closes. Okay, 1 2 operated with 1 2 3. Cycle is closing. Okay, so now let us see what is the image of 2. So 2 is mapped to 3 and 3 to itself. So 2 is mapped to 3. For surety, let's find the image of 3 also. So 3 is mapped to 1 and 1 is mapped to 2. So obviously 3 is mapped to 2. So this is equal to 2 3. Cycle 2 3. So we are having cycle 2 3 here. Now when you will operate 1 2 with 1 3 2, you will find we will be getting 1 3 here. Okay, you can do it and you can find it out that we will be getting 1 3. Alright, now 1 2 operated with 1 2. Let us see what does this give. So here you can see 1 is mapped to 2 and here 2 is mapped to 1 again. So we are having like this. For 2 similarly 2 is mapped to 1 and 1 is mapped to 2. So 2 is mapped to itself and 3 is nowhere present in the cycle, so 3 is fixed. So we get identity permutation. So here we are having I. Now let us see what is 1 2 1 3. 1 2 1 3 is 1 is mapped to 3 and 3 is mapped to itself. So this. Now let us find the image of 3. 3 is mapped to 1 and here 1 is mapped to 2. So 3 will be mapped to 2. For surety, let us find the image of 2 also. So 2 is mapped to 2 itself and here 2 is mapped to 1. So the image of 2 will be 1. So we will be having 1 3 2 here. Alright. Now when you will find what is 1 2 2 3, you will see that we will be getting 1 2 3. Okay. That is the only element left, that is y, and also when you will calculate you will see that we will actually get 1 2 3. Okay, so this is how we can fill the fifth row or fourth row. Fourth row. Now here of course we will be having 1 3 itself, and now let us see what will be here. So I'm writing here 1 3 operated with 1 2 3. Okay, so 1 is mapped to 2, 2 to itself. So the image of 1 will be 2. Now 2 is mapped to 3, 3 is mapped to 1. 2 is mapped to 3, 3 is mapped to 1. So 2 will be mapped to itself and you will find 3 is kept fixed. So this is what we will get 1 2. Okay, so here we will be having 1 2. Okay, so this is 1 2 and here you will find it will be actually nothing but 2 3. Okay, this will be nothing but 2 3. Now 1 3 1 2. Okay, this will be equal to 1 is mapped to 2, 2 is fixed. So the image of 1 is 2 itself. Now 2 is mapped to 1, 1 is mapped to 3. So here we will be having 3. So 1 2 3. This is what we will get. So here we will be having 1 2 3. Are you sure? 1 is mapped to 2, 2 is mapped to itself. Yes. Now 2 is mapped to 1, 1 is mapped to 3. So this 3 is fixed and 3 is mapped to 1. Right. Okay, so we will be having 1 2 3 here. Now 1 3 with 1 3. You will find that it will be equal to identity in a similar manner by which we found 1 2 operated with 1 2 gives identity. Alright, so here we will be having identity, and in the similar manner when you will calculate you will find 2 3 operated with 2 3 itself also gives us identity permutation. Okay, so this is what we have. Even though we have not found the identity of S3, I'm still writing our cycle 1 2 3 with 1 2 3 as identity permutation, simply because while doing the operations with permutations we can easily find that This is the identity permutation. This is the permutation which when operated with any other permutation keep that permutation fixed. Okay, so that is why keep that permutation as it is. Now let us find what is 1 3 2 3. So let us find the image of 2 here. Okay, so 2 is mapped to 3 and 3 is mapped to 1. So 2 is mapped to 1 and now 1 is mapped to itself and here 1 is mapped to 3. So this is what we have. Okay, and this permutation is same as 1 3 2. Okay, you can write it like 1 3 2 itself. Say you have a permutation A B C, then this is similar to BCA and this is similar to CAB. Alright, just make sure that after A you are having B and after B you are having C. You can change which will come first and which will come last. Okay, so and this is possible for cycle of any length. Alright, for any length like x1, x2, xn length also. This will hold true. So, yes. So this will hold true for cycle of any length. And now we saw that we got 132. Okay. So let me write 132 here. Here again I will be having 2 3. And now we have to find what is 2 3 operated with 1 2 3. So we have to find what is 2 3 operated with 1 2 3. It has become very clumsy. So 2 3 operated with 1 2 3 will actually give you 1 3 and 2 3 operated with 1 3 2 will give you 1 2. You can find them out. You can do the calculations. You will find this itself. Now 2 3 operated with 1 2. We have to find what is this equal to. 2 3 when operated with 1 2. So 1 mapped to 2, 2 to 3. So here 3 is fixed, 3 mapped to 2. So 1 3 2 is what we have. And here we will be having 1 2 3. You can calculate and find it out. So this is how the table looks like. Okay, this is how the permutation table, the composition table looks like. And now using this composition table, we will actually see whether S3 is forming a group or not. And for that, let me just erase few of the things so that we can write on this slide itself. And there is no need to change the slide. So now we will see whether S3 forms a group or not. Now from the composition table, one thing which you can conclude easily is from the composition table, one thing which you can conclude easily is all the elements in the composition table are the elements of S3 itself, right? All the elements in the composition table are the elements of S3 itself, and therefore clearly closure property is satisfied. Because obviously if you operate any two elements A and B from S3, you find A star B belongs to S3, right? For AB belongs to S3, we have A star B in S3. So S3 is closed with the operation composition, and therefore we can say that the first condition to be a group, that is the operation should be a binary operation, is holding true. Now we have to check the other properties, that is the associativity. So for associativity, you can take any three elements from S3, any random three elements from S3, and you can see that A star B star C is same as A star B star C. Alright, so basically the operation of function composition is associative. You can apply this associativity on any elements and you will see that it is holding true. Okay, so associativity is also holding true. Now two properties are getting satisfied, and the third property is the existence of identity element. So clearly while making the composition table, you can observe that this particular element identity I, which is basically the permutation, this is the identity element in S3 because I operated with any element A of S3 gives you A itself. I operated with I gave you I. I operated with 1, 2, 3 gives 1, 2, 3. I with 1, 3, 2 gives 1, 3, 2. I with 1, 2 gives 1, 2 and so on. And similarly, A star I gives you A again. I with I gives you I. 1, 2, 3 with I gives you 1, 2, 3. 1, 3, 2 with I gives you 1, 3, 2 itself and so on. So you can see that the first row and the first column is identical to the elements at the top and the elements at the leftmost respectively, and therefore I is the identity element. So we have identity element in the group. Now the next property is existence of inverse, and now let us specifically write which element is the inverse corresponding to which element. So let us first write the element, and here I will be writing the inverse. So here you can see that identity element will be obviously having its inverse as I itself, right? So the inverse of identity element is itself. Now for the remaining elements, let us find what is the inverse of 1, 2, 3. Now to find the inverse of 1, 2, 3, consider 1, 2, 3 and start moving in the row. Start moving rightwards and stop at the place where you get I, the identity permutation. So this is the place where you got I, and find which element is at its top, and you can clearly see it is 1, 3, 2. Therefore 1, 3, 2 will be the inverse of 1, 2, 3. Okay, so here we will be having 1, 3, 2 as the inverse of 1, 2, 3. The simple reason is because 1, 2, 3 with 1, 3, 2 gives you I, because here we are having I, and similarly you can observe 1, 3, 2 with 1, 2, 3 gives you I again, and the reason for that is 1, 3, 2 operated with 1, 2, 3 gives you I. Alright, so the inverse of 1, 2, 3 is itself. Now if 1, 2, 3 is the inverse of 1, 3, 2, what will be the inverse of 1, 3, 2? Obviously 1, 2, 3. So the inverse of 1, 3, 2 is 1, 2, 3. Now we will find the inverse of 1, 2, 2, 3 and 1, 3. Okay. So again look at the composition table. Choose 1, 2, start moving rightwards and stop at the place where you get identity element. And here is the identity element, and the element at the top is 1, 2 again. So basically the inverse of 1, 2 is 1, 2 itself. You can clearly see 1, 2 operated with 1, 2 gives you identity. Alright, because 1 is mapped to 2, 2 is mapped to 1. So here we will be having 1. 2 is mapped to 1, 1 is mapped to 2, so 2 again. So this is the identity permutation. So the inverse of 1, 2 is 1, 2. Now inverse of 1, 3, similarly start moving and stop at the place where you get identity element. You can see 1, 3 is at its top. So the inverse of 1, 3. Okay, so we are finding the inverse of 1, 3. So it is 1, 3 itself, and for 2, 3 also it will be itself. In fact, if you consider cycle of length 2, which is of the form some AB, then its inverse will be AB itself. Alright, if you consider any cycle of length 2, not only in S3 but any permutation over n letters, the inverse will be itself. Okay, when we are having the cycle of length 2, specifically the cycle of length 2. It is not in the case of cycle of length 3. You can see the inverse of 1, 2, 3 is 1, 3, 2, and for 1, 3, 2 it was 1, 2, 3. So the inverses changes. If we are having a cycle of length 2, the inverse will be itself. Okay, so these are the inverses. And now let us find the order of each of the element. So for the order, let me just make a column here itself, right? Yes, order. So clearly the order of identity element will be 1, right? Now, what is the order of 1, 2, 3? So let us find that. 1, 2, 3 operated with 1, 2, 3. What does it gives you? 1, 2, 3 operated with 1, 2, 3 gives you 1, 3, 2, which is not equal to I. So clearly order of 1, 2, 3 is not equal to 2. Now 1, 2, 3, 1, 2, 3 and again 1, 2, 3. This is basically equal to 1, 2, 3 and this is 1, 3, 2, right? When we operate 2 times, we get 1, 3, 2. So this is what we have. Now what is 1, 2, 3 operated with 1, 3, 2? Obviously identity, we even saw here. They are inverses of each other. So this is giving us I, and so order of 1, 2, 3 is 3. Okay, so the order of 1, 2, 3 is 3. Now what is the order of cycle 1, 3, 2? You can clearly find, because 1, 2, 3 is having 1, 3, 2 as its inverse, and the order of an element and the order of its inverse are always same. So the inverse of 1, 3, 2 will be also 3. Now what about the inverses of these 3 permutations? Now I told that the inverse of cycle of length 2 is itself. If you are having any cycle of length 2, it will be its own inverse, and therefore they are self-invertible. Alright, so they are self-invertible. That is, if you are having any cycle of length 2, you operate with itself, you get the identity permutation. Alright, you can say A is mapped to B and B is again mapped to A. So you will be having A, B is mapped to A and A is again mapped to B. So B, and that is why this is the identity permutation. So they are self-invertible and clearly therefore their order will be equal to 2. So the order of these 3 permutations is equal to 2. So this is about the order of the elements of S3. Alright, so these are the order of elements of S3. These are the inverses of the elements. Then we saw that composition. The function composition is a binary operation, and for associativity, just take any 3 elements and just put say 1, 2, 1, 3 and 1, 2, 3 and find whether you are getting it equal to 1, 2 and then 1, 3, 1, 2, 3. Just remember how you have to operate. You will find that associativity is holding true. It is not possible to check the associativity on each and every element, but because we know that actually these are permutations, and permutations are nothing but 1, 1 onto functions from a set to itself, and the operation is function composition, and we have already been studying that function composition is associative for any function f, g, h defined from a set to itself. F composition g composition h is equal to f composition g composition h, right? So for obvious reasons the function composition will be associative on the set, and therefore associativity holds true. So all the four properties are holding true. S3 forms a group. These are the inverses of each and every element of S3, and this is the order. So that's all for now. Thank you.